Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Yeah, hello and Happy New Year. I would like to welcome you to our AI for Good seminar. My name is Wojciech Samek. I'm professor of machine learning and communications at Technical University of Berlin and also the AI director at Fraunhofer Heinrich Hertz Institute in Berlin. And it's a great pleasure for me to introduce today's speaker, Al-Hussein Fafsi. Al-Hussein is a research scientist at Google DeepMind. He obtained his PhD from the Signal Processing Lab in EPFL in Switzerland in 2016, and his Master of Science degree in Electrical Engineering, also from EPFL in 2012. His main research interest lies in using AI for the sciences, in particular on using machine learning to unlock new results in mathematics. And today's talk, he will present his recent work on AlphaTensor, and I very much look forward to your talk, Hussein. So the stage is yours.
Thank you very much for the invitation. It's a great pleasure to be here. And thanks for the intro. So today I'd like to talk to you about our recent paper on discovering new algorithms using machine learning, and in particular using reinforcement learning. Okay, so we'll be focusing on the topic of matrix multiplication in particular, as we'll come to. So the project really started with a very simple question, which is as follows. Can we discover new, provably correct and efficient algorithms for impactful problems using machine learning? Okay, so there are a few keywords here. Provably correct, meaning that we're looking for algorithms that are correct for all instances, not only, for example, for a particular distribution of data points or for which you don't have any guarantees. We're looking for something where you can get a certificate of correctness for all instances. Efficient, meaning that we really want to find like algorithms with good computational complexity, or with like that actually run fast on a specific hardware. And the third keyword is impactful problems. So we're looking for these, what we call root node problems, that if you're able to find new algorithms for these root node problems, then this would unlock many other problems. Okay, so now if we're able to do this, if we're able to discover new provably correct, efficient algorithms for impactful problems using machine learning, then the impact of this can be huge. Because if we're able to automate this process, then we could like improve the efficiency of the algorithms that are used everywhere, from your smartphone to supercomputers. These algorithms are really used everywhere, right? But it's not an easy task. It's not very easy to say the least, to automate the procedure of algorithmic discovery and to use machine learning for finding these algorithms. Why is that? Well, because we're looking for, as I said, we're looking for provably correct algorithms. And if you think about the space of provably correct algorithms, then how do you even start formalizing what is this space of provably correct algorithms in which you want to search in, right? So this is a very difficult task of formalizing the process of algorithmic discovery itself. Now, even if you're able to formalize the space of algorithmic, the space of algorithms in which you're interested in, then the search space in which you're going to to search in is going to be huge, right? So there is also like a fundamental number of challenges which we'll come to during the talk about the scale of things. Like the search space is very large, and how do you go about doing that? Okay. So as I said, we're going to focus on the topic of matrix multiplication because I think you'll all agree that matrix multiplication is a root node problem in the sense that it's perhaps the most fundamental computational task that is used obviously from like solving linear systems to simulation to training neural networks to many applications. So the outline of my talk is going to be as follows. So first, we'll go through formalizing the problem of matrix multiplication, of finding algorithms for matrix multiplication as a machine learning problem, right? So it's not direct. How do you do this? As I said, this is one of the difficulties of like, how can you translate the problem of finding, discovering new algorithms to a computational problem for which you can use the techniques such as reinforcement learning to search for. The second part of my talk is going to be about addressing the challenges that I talked about, like in particular the scale challenge that are needed to make machine learning work for this particular problem, but also like discuss like different hopefully like the ingredients that I'll give are also relevant for other math problems. And then I'll go through the results and we'll have concluding remarks later on. Okay. So first things first, let's like go through what matrix multiplication is. I'm sure you all know what matrix multiplication is, but just to set the notations right. So here we have like two by two matrices that you want to multiply, matrix A and matrix B, that is equal to matrix C. The process of matrix multiplication is written on the right here. Okay, so you're going to do A11, B11, and A12 times B12, and then you're going to add these together to C11. Okay, so this is the process of matrix multiplication for 2 by 2 matrices, and this is what we've been taught in high school, right? And for a very long time, it was believed that this is the best way of doing matrix multiplication. There is no algorithm that is better than that for getting this matrix C out of the matrices A and B. But a German mathematician called Volker Strassen in 1969 shocked the mathematical community and showed that there is actually a better way of doing matrix multiplication than the standard algorithm that we're taught in like the standard classroom algorithm. And the way one could do this for 2 by 2 matrices is by combining entries of A together, entries of B together, and then like multiplying them in a weird way, and then distributing them again like in a quite an obscure way, and then you get the good result. So that's like, it's quite difficult to come up with such an algorithm, but it's very easy to check, right? Because like you can do the arithmetic calculations, and you precisely get the correct answer. Okay, so Strassen's algorithm, the important bit here is that Strassen's algorithm involves 7 scalar multiplications as opposed to 8, right? So here you really need to do 8 multiplications when you do the matrix multiplication of 2 by 2 matrices, whereas Strassen uses only 7. Okay, so why is that interesting? Well, it's interesting because Strassen's algorithm can be used recursively. So it's not only applicable to 2 by 2 matrices. Let's say you have you want to multiply n by n matrices. Then what you can do is you separate your n by n matrices into 4 blocks of size n over 2 times n over 2 each, and then you apply Strassen's algorithm, and then you apply it recursively and so on till the very end. And it's not very hard to show that the complexity of this algorithm is n to the power log base 2 of 7. Okay, 7 here is the number of multiplications. Okay, so remember that like Strassen's algorithm involves 7 scalar multiplication, and you do it recursively. Therefore, you get this log. And so what you get is an algorithm of complexity n to the power log base 2 of 7, which is roughly n to the power 2.81, which is better than the standard algorithm, which is cubic, n cube. Okay. So this was really like, this shook the mathematical community, as I said, and And then like it was open from that point, like, okay, what is the best algorithm for you to do matrix multiplication? Now, when I first learned about this algorithm, Strassen's algorithm, I realized that, I mean, potentially Strassen was able to do this, like he was able to do this like on a piece of paper, but this is very hard. Like even like for 2x2 matrices, it's quite hard. So what about 3x3 matrices, 4x4 matrices, and so on? This becomes even harder and harder. And I think machines are much better at finding these algorithms, as we'll see, than what we can do. So let's try to formalize a bit this operation of matrix multiplication and how we can formalize the process of discovering new algorithms as a search problem. Okay, so first, the operation itself of matrix multiplication. So just like linear operations, you can represent them as matrices. Bilinear operations, and matrix multiplication is one bilinear operation, you can represent them as tensors. Okay, so bilinear operations, you can represent them as tensors, just like linear operations, you can represent them as matrices. Okay, so in like more quantitative terms, the operation of multiplying two n by n matrices, you can represent by a tensor of dimension n square by n square by n square. Okay, so this is, for example, the tensor that represents the operation of multiplying two 2x2 matrices. As I said, this is a tensor of size 4 by 4 by 4 because n is equal to 2 here. And I'm emphasizing about the fact that this tensor is representing the operation of multiplying matrices rather than the matrices itself, right? So it's independent of the matrices that you want to multiply. This is really at the operator level. So it's one tensor that represents the operation of multiplying matrices. Okay, so it's a tensor of like where the cells are either 0 or 1. Okay, and the cell is equal to 1 if there is if you're going to do a multiplication, essentially, and so essentially, like you have a cell that is equal to 1 here. For in this example, it's represented with a blue cube, which tells you where to read the multiplication from and where to write it. Okay, so here, for example, you're going to read the multiplication from A21 and B12 because you're going to do that operation, and then you're going to write it in C22. So therefore, you're going to put a 1 in the cell corresponding to coordinate A21, B12, C22. Okay, and same for this one, where you're going to put again like a 1 at A22, B22, C22. Okay, so therefore you have a tensor of size 4 by 4 by 4, which represents entirely the operation of multiplying two 2x2 matrices, again independent of the matrices you want to multiply. It's a tensor of size 4 by 4 by 4. It has 8 ones, as we saw, because like it has 8 multiplications, and the rest, all the other entries are equal to 0. Okay, so this is the operation of multiplying matrices. How can we formalize the algorithms to multiply matrices? Okay, so what we'll be looking at here are families of algorithms that are obtained by a decomposition of this tensor, or by a tensor rank decomposition of this matrix multiplication tensor. Okay, so first things first, what is a tensor rank decomposition? Well, it's actually very similar to what you know, like a matrix rank decomposition, except that there is a third mode, right? So you remember, like if you have a matrix and you want to decompose it into a sum of rank 1 matrices, then you write it as sum of UQ VQ transpose. Here I have an operation which is like the tensor product, which generalizes this outer product because we have like 3 modes now. Okay. So it's exactly, as I said, it's exactly a simple generalization. So you want to find the decomposition of T into a sum of rank 1 tensors. Each rank 1 tensor is equal to a UQ, tensor product VQ, tensor product WQ, where UQ, VQ, and WQ are vectors. Each one is a vector of size n square. Okay, and therefore each rank 1 tensor is of size n square by n square by n square. Okay, so I'm claiming that if you have a low rank decomposition of this tensor, then you automatically get an algorithm for multiplying matrices. Okay, so this is just on the bottom of my slide is just a pictorial representation of what a tensor rank decomposition is. So how can we go from this tensor rank decomposition to an algorithm? Well, it's actually quite simple. If you're given two matrices A and B that you want to multiply, then what is shown on the right here is precisely the algorithm that you need to do in order to multiply matrices A and B, okay? Now, the important quantity here is the rank, okay? So the rank characterizes the complexity of this algorithm, okay? So, and these algorithms, they can be used really recursively, right? So just like Strassen's algorithm, he derived an algorithm for multiplying two by two matrices, and then he used it recursively. We can do the same thing. We can derive an algorithm using this tensor rank decomposition, and then we can apply this recursively for any metric size. Okay. So let's see more in detail, maybe the relation between the rank and the actual algorithm for Strassen's case. So Strassen's result for multiplying two by two matrices can be reframed as just saying that the matrix multiplication tensor for multiplying two by two matrices is of rank 7, not of rank 8. Okay. So that's just the new way of saying it with this tensor language I just described, okay? So what this means is that there is actually a very nice correspondence that you can have. So for example, the first line of the algorithm here corresponds to summing A11 plus A22 and then multiplying it by B11 plus B22. There is a direct correspondence here with the first factor because the first factor is like 1001. It tells you which A's you add together. The second factor here tells you which B's you add together. And then the third factor here tells you how do you distribute this H1 that you just computed into the different outputs, okay? So you can have this direct mapping between the algorithm form and this tensor decomposition form. Okay. Okay, so now we started with this goal of finding new algorithms for matrix multiplication, and now we converted it into a problem, into a math problem, which is to find low-rank decompositions of the matrix multiplication tensor. Now, unfortunately, unlike matrices where the rank is really like there is a polynomial time algorithm to compute it, when you start to be three-dimensional, then it's becoming really hard, and there is no way of, or like there is no polynomial time algorithm to compute the rank or good rank decompositions of these tensors. So this is precisely where we're going to use machine learning for, to tackle the problem of tensor decomposition for the specific tensor of matrix multiplication. Okay, so how are we going to model this? So we're going to model this as a game, right? As a single player game. And our board is going to be this tensor, this matrix multiplication tensor. We're going to start at least the board with this matrix multiplication tensor. So it's a 3D board. And then at each step, what the player can do is to subtract a rank 1 tensor. Okay, so the player, what he does is to choose a rank 1 tensor and then to subtract it from this board, from this current tensor. Okay, so then you update the board. Okay, and then you repeat. Okay, you repeat, and the player wins if you arrive to the 0 tensor. If you get the tensor that is made all of zeros. Okay, it's not very hard to see that whenever you reach the 0 tensor, then you precisely get an exact decomposition of this matrix multiplication tensor, and therefore an algorithm for multiplying matrices. Okay. Now, we don't want just to find any decomposition of this matrix multiplication tensor. We want to find the a low rank decomposition of this tensor. So therefore, what we do is that we give a -1 penalty, like a -1 reward at each step, okay, that the agent takes. Okay. Now, also, if let's say the agent the player plays a game and then doesn't arrive to the 0 tensor at the very end, doesn't reach the 0 tensor at the very end, then you have to give a penalty, which is an upper bound on the rank of the residual tensor. Okay, and you can do that quite easily. Okay, so this is how we can model this problem. Now, as I'll go through, there is a few difficulties associated to this, to solving this this game. The first one is being like that there is a huge action space, as we'll see. There is no training data. There is only one tensor to decompose. Remember that we care only about this matrix multiplication tensor. Whenever we decompose that, then we get an algorithm for multiplying arbitrary matrices, like provably correctly arbitrary matrices. And then there is tensors have a lot of symmetries, so it can be either seen as a difficulty or as something positive, where tensors have a lot of symmetries. So how do you best incorporate these symmetries into your machine learning model is also something that requires some thinking. So let's have a small comparison between like this environment and the environment of Go, for example. Where really the main difference here is, as I said, on the action space. Actually, in theory, this game has an infinite action space because the number of rank 1 tensors is infinite. Now we do discretize the problem by considering, for example, rank 1 tensors where the factors have -1, 0, 1 or -2, -1, 0, 1, 2, and so on. So we do discretize it, but even when you discretize it, then the action space really blows up. So for example, for the case of the 2x2, which we talked about for a long time, if we decompose that into a rank 7, then we recover Strassen's algorithm, you have an action space which is 10 to the 8. The number of rank 1 tensors that you need to choose at each step is 10 to the 8. Compared to Go, the board size is 19 by 19, and you have roughly like 362, or you have exactly 362 actions, so 19 times 19 minus 1, plus 1. And so you can see that there is a large difference here in action space. So we really need something novel to go beyond these numbers that were considered in Go. And if you consider like larger tensors, like for multiplying 3 by 3 matrices, 4 by 4, 5 by 5, then the action space like really blows up, and you cannot enumerate anymore all the actions at each step. So the approach that we're going to take here is as follows. So we're going to at each step of the game, essentially, we're going to do a lot of simulations and try to see, try to evaluate using a neural network what is the most promising rank 1 tensor to subtract. Choose that, do a lot of new simulations in a Monte Carlo tree search fashion, and then select the best rank 1 tensor, and so on and so forth. Okay, so this animation here is done for Go, but as you can imagine, for this game, you cannot just enumerate everything. So you'll have to this animation is like much bigger for this particular case, and you cannot really go through all of them. Okay. So so AlphaTensor, our agent to solve this problem, is based on AlphaZero, and so I'll describe now briefly what AlphaZero is. So AlphaZero is this algorithm that has been developed by DeepMind, which has superhuman performance on chess and Go and some other games, but it's a general algorithm that can really be used in different settings, and we'll be building on that here. So the main idea behind the algorithm is that there is two components. Okay, there is like actors and a learner. Okay, and what the actors do is that they play a lot of games independently. So think of many different computers playing games like, for example, Go or this tensor game which I just presented, like independently. Each computer plays it independently. Okay, at each step, you're going to do a tree search to identify what is the most promising rank 1 tensor, or like what is the most promising move. You're going to apply it, and so on and so forth. Okay, so at each step, what I want to emphasize on here is that at each step, you're going to do a tree search, and we're going to see how we can use machine learning to guide that search. Because, like, obviously, if you try to do exploration randomly, then you're not going to be able to get anywhere. But that's how things start. So in the beginning of the training procedure, actors play or like do some random simulations, So the games that they generate are not very good. Like the decompositions they find, for example, are actually quite bad. But still, like we're going to send these games to the learner. Okay, so these games that are not very good, we're going to send them to the learner, and then the job of the learner is to take in those games, those states that make up those games, and then to try to mimic the moves that have been played by these games. Okay, so in particular, we're going to try to predict two things as the output of this neural network. The first one is the policy. The policy is just a prediction of what was the next move. Okay, and it's going to try also to predict a value, and the value is an estimate of how good my state is currently is. Okay, so for example, in the case of tensor decomposition, the value corresponds to an estimate of the rank of my current tensor. Okay, so I'm going to therefore try to train a neural network, or like do some steps to train this neural network to mimic the games that have been sent to me by the actors. Okay, try to predict what was the next move that was taken, and to try to predict the interestingness of the current state at which I am. So I'm going to do a few gradient steps, and then I'm going to send that network to the actors again. Now the actors are going to try to use that neural network to improve a bit on the games that are generated in the first iteration. Okay, so in the tree search that I'm going to do at each step to select what action I'm going to choose, I'm going to be guided by that network. Okay, so I'm going to be guided by that network, but I'm not going to follow it like blindly, right? So I'm going to try to improve a bit over the outputs that are given to me by the network. Okay, so you can think of the tree search that you're going to do at each step as a policy improvement operator, right? So you can think of the network that is given to the actors as some sort of baseline, and then by doing a tree search, you're going to try to improve a bit over that. Okay, you're going to play games, and then you're going to send that again to the learner, and then the learner will be trying to mimic that again, and then sending it to the network, and then hopefully like you improve through this tree search over the outputs of the network, and so on and so forth. So that's a self-reinforcing loop where the actors generate better and better games. The learner makes sense of this data and also improves, and so on and so forth. Okay, so that's the algorithm behind like this huge improvements in games like Go and chess, and we're going to be based on this procedure here. Now, if we use this completely out of the box, then as I said, there are a number of challenges. So now what I'll be going through is like 4 ingredients, which I think are important for they were very important for solving this problem, but I think they also like go beyond this particular problem and can be useful in many math and computer science problems. So the first ingredient I want to go through is synthetic demonstrations. The second one is to diversify the target. The third one is to train a generalist agent. And then the fourth one is a deep and tailored architecture. Okay, so let's go through these. The first one is synthetic data. Now, unfortunately, in many math problems, we don't have a lot of data, so we need to rely instead on synthetic data, right? So now, fortunately, the tensor decomposition problem, and I think many other problems, fall under the category of like being one direction is really hard, but the other direction is quite easy. Okay, so for example, in our case, it's really hard to get a decomposition from a tensor, but the opposite way is actually very easy. You can generate like some random decompositions, and then you sum them together, you get the tensor essentially. So it's really easy to go from decomposition to tensor. So in that way, you can generate an infinite training set that you could use for training in addition to the data that has been generated by the actors. Okay, now the nice thing also about this is that you can incorporate symmetries of the problem in the synthetic data. So for example, let's say that you care about decompositions that have some symmetry. For example, if you have a factor that is UVW, then you also have VWU and WUV and so on. Then you can incorporate that in the synthetic data, and therefore the neural network will be biased to output decompositions that have these symmetries. Yeah, so as I said, we trained this the network on data coming from actors in addition to the synthetic data. And obviously, like one of the potential issues with this approach is that the distribution of synthetic data can be quite far from that of the target. So remember that what we care about is decomposing that matrix multiplication tensor. But what I'm saying here is to generate synthetic data that is random, right? So you generate random decompositions and then you form the tensor, their tensor. So you have these pairs of tensor and rank decomposition that you can use as demonstrations. But yeah, this is very different from the matrix multiplication tensor, which is very symmetric. Nevertheless, we found this to be a very useful approach, especially at the beginning of training. The second ingredient is to diversify the targets. So remember that we care about decomposing one specific tensor, the matrix multiplication tensor, and that's I think a common thing we have in many math problems, which is that you care about proving one theorem, you care about one particular use case, and this is quite different from problems in machine learning where you care about the average performance across many data points, right? So how do we go about like translating this problem where you care about one thing to caring about really or like to a usual machine learning problem? Well, what we can do here is to express the tensor in different bases, right? So just like for matrices, if you apply a change of basis to the matrix, you have the same exact rank. You can do the exact same thing for tensors. So you have this matrix multiplication tensor, you apply a random change of basis, you have a new tensor, so completely new numerical values. And it is guaranteed that they have exactly the same rank, but the network can leverage from the diversity of this, because obviously the neural network is not aware that this tensor is like equivalent to the original matrix multiplication tensor. So pictorially, you can think of this as getting closer to the training data, to the random training data, which I was discussing before, and in the sense that if you're able to find a good rank decomposition for any of the dotted circles here, then you can propagate that information to all others, because what you can do is just to apply an inverse change of basis, and then you get a good decomposition for all these targets. The third ingredient, which we found to be very useful, is to train generalist agents rather than several experts. So what one can do is to say, okay, like I want to train a neural network to find low rank decompositions for the 2x2 matrix multiplication tensor, essentially trying to rediscover Strassen, for example. You can do that, but what works really best, especially like for difficult targets, is to just train one agent that solves all the problems, all the different sizes at once. And what you will see is that there is positive transfer between the different targets. So for example, the agent will will decompose the 2x2 matrix multiplication tensor fairly quickly, and then transfer the information to some other targets and so on and so forth. So you see this positive transfer and some sort of like curriculum happening, although we didn't impose anything about the curriculum, automatically. And what's also interesting is that there is transfer between targets that we thought were not mathematically related, or at least we don't have any mathematical relation between them, yet it was very useful to have them trained together. Okay, so for example, I don't know, I'm just making this up, but 2x2 times 2x2 matrices with like 3x3 times 3x4. So if you train these together, then it will be much better than if you train each one separately, although we don't have any mathematical relation between them. Okay. So this was very important to get our results. So yeah, I mean, this has the training generalist agents has the advantage of getting better results, but also being much more efficient because you just train one agent to solve all your problem, or your different sizes, and even beyond. We actually just trained one agent to solve different fields too. So you can consider, like, let's say you want to find algorithms for multiplying matrices in a certain field and in R, then you can train these two together and the different sizes also together. Then this works better than if you focus just on one specific field, because there might be transfer between different fields. Okay, the fourth ingredient is to train large and deep tailored neural networks. So remember that the neural network has this architecture, which is like the idea of the neural network is to output two things: the policy, which is the next move, and the value, which is an estimate of the rank, right? So the architecture is like, we have a common torso, and then we have two heads to output these two things. And it's very important. It was very important to focus on the architecture of the torso and to try to embed prior information about the tensor, like about tensors in general. So tensors have a lot of symmetries. Like, for example, if you permute two slices of the tensor, for example, then you have the same rank, right? So the idea is to try to embed some prior information about tensors in the torso. Okay, so what was the architecture that we used? So the first thing we do is to project this tensor, this n squared by n squared by n squared tensor, into three grids of features. Okay, so the main motivation behind this was really like computational, because like working with large tensors is quite computationally intensive, and especially that we want to do a lot of simulations. So the way we do that is to, as I said, we project into three different modes. And you can think of the three different modes as being like different viewpoints of your tensor. Okay, so you project into the mode U and V, the W and V, U and W, which are supposed to represent different information, different viewpoints of your tensor. And then what we do is some attention operations on sets of features belonging to a pair of grids. Okay, so we have these three grids now. Now, what we can do is to do attention between every cell and every other cell, but this worked worse and doesn't incorporate so much maybe prior information than as opposed to doing this thing, which is to do attention between the cells in red here. Okay, so you take all the cells that belong to one slice, and then you attend between them, do some attention operation between them. And the idea here was that elements that belong to one slice are more related to each other than elements that don't belong to the same slice. Okay, so that's why we do the attention between these elements belonging to the same slice. Okay, and you do that for all the different pairs of modes. Okay, now, so the overall system here is as follows. So as I said, you start with this matrix multiplication tensor, you do a change of basis, a random change of basis, you do the like Monte Carlo tree search based on the current neural network you have, you play the game, you generate you send the game to the learner, and then the learner is going to train itself from two separate sources. One is this buffer of games that have been sent to you by the actors, and then the other source is pre-generated synthetic demonstrations. You're going to sample a random state. You're going to train the network to predict essentially like either the next move from the synthetic demonstration or the next move from the game that has been played by the actor. You're going to update the model, and then you're going to send it to the actor, and hopefully, like with this like iterative approach, you're going to improve. So that's that's about the method of AlphaTensor. So now I want to spend some time to talk about the results. So as I said, we trained one agent to decompose all the different tensors, like from 222 to 555, which correspond to multiplying n by m times m by p matrices. Okay, And obviously, because matrix multiplication is very well studied, it's well tabulated essentially for each n by m times n by p. What is the best algorithm in terms of like the number of multiplications or the rank to do this multiplication essentially? Okay, so for example, for multiplying 2 by 2 matrices, the best known algorithm, and actually like provably, is Strassen's algorithm. You cannot go beyond that. So the rank is precisely 7 for 2 by 2 matrix multiplication. We know we cannot improve that, but starting from starting from 3 by 3, then it's really like unknown. We don't know the rank of these matrix multiplication tensors. Okay, so and as I said, you train AlphaTensor also on different fields. So you train it on fields of characteristic 2 and on R, like jointly. And what happens is that in the beginning of training, you get like you don't get like any algorithm. Then you get the standard algorithm for multiplying matrices, and then you discover Strassen's algorithm, and then bit by bit you recover the existing known results, until at some point you surpass, like here, for example, 3 by 4 times 4 by 5 matrix multiplication. You improve the result by 1. So it found an algorithm for multiplying 3 by 4 times 4 by 5 multiplications using 47 scalar multiplications. And you continue, it improves even more and even more for larger matrix multiplications. So these are the examples where the machine learning discovered algorithms are outperform the known algorithms. And one particular result we were surprised with was that we were able to, for the first time, improve the 4 by 4 matrix multiplication in fields of characteristic 2. The best known one was the same as like from 1969, was Strassen's algorithm applied twice. So you apply like Strassen 7 and then 7, so you get 49. But here we were able to break this and to go beyond the 49 operations and find algorithms that only involve only 47 multiplications. Okay, so how do these algorithms look like? So this is, for example, this rank 47 matrix multiplication in fields of characteristic 2. So you can have a look at it. As I said, these are kind of algorithms that are quite hard to interpret, but very easy to check, right? So you can do the arithmetic operations, and I mean, obviously by hand, this is also quite difficult to do, but using a computer, it's quite easy to check that the correctness of this algorithm. Beyond that, it's quite, I think, hard to interpret, or at least for me, to interpret why the agent chose to add A11 plus A31 plus A33 and do times B11 plus B31 plus B33. It's hard to go beyond that, other than it just works like when you write it down. So for each row that I showed in the results, we don't actually find just one algorithm. We find like thousands of inequivalent decompositions for each target, okay? And we open source this data set of factorizations of algorithms. And I think this is very useful to help us better understand the space of matrix multiplication algorithms. So for example, we could show that the space of matrix multiplication algorithms is much richer than what was thought before, in the sense that, I mean, I don't have time to go through what does it mean to be inequivalent, but essentially, like, there is a group of symmetries that you can apply to your algorithm, and that conserve the correctness of matrix multiplication. So what we can show is that there is a lot of algorithms that go beyond this group for many of the sizes. So we think this can really help understand better the space of what does it look like, the space of matrix multiplication algorithms. Now, the other benefit of having diverse matrix multiplication algorithms is that you can recombine them together and then find good algorithms for larger tensors. So we have some divide and conquer approach where you can recombine two algorithms from the ones that we generated, and then surpass essentially like the state of the art for larger for larger matrix multiplications, larger than 555. I mean, and the results are shown here on the right, like in terms of like what are the improvements for these tensors. So I have like a couple, like 5 minutes. I guess I'll probably finish in 5 minutes or like 4 minutes. Try to finish. Keep 10 minutes for questions. So the approach that we used is not really specific to matrix multiplication in the sense that we can take any tensor and then we decompose it essentially. So you can think of any bilinear map and then find decompositions of this bilinear map and then therefore find algorithms for the operation for the bilinear map that you consider. So for example, to illustrate this, let's take the example of skew-symmetric matrix vector product. So that's a specific bilinear operation. So what you can do is to use AlphaTensor to decompose this operation for n is equal to 3, n is equal to 4, n is equal to 5, 6, and so on. And then you can see clearly that there is some pattern happening, and you could extrapolate this pattern and then essentially write down the algorithm and verify its correctness. And the algorithm that we find is actually going beyond the best known result for the specific case of skew-symmetric matrix vector product. You could do the same thing for circulant matrices, for example, and then recover the Fourier basis, which is also something we do in the paper. Now, there is also like our approach is also quite general in the sense that you don't like what we did is to optimize the rank, but you can go beyond that really because we use reinforcement learning, and as long as you have something computable, then you can use it in your reward function. So we said, okay, let's try to use a wild reward function, which is the actual runtime of the algorithm on a hardware. Okay, so we do the same thing as what I described previously, except that at the very end, we're actually going to take this algorithm that was found, run it on a specific hardware, and then get some latency results, and then try to favor algorithms that have low latency. Okay, and the algorithms that you find are like for multiplying large matrices are better than the standard algorithms that are used in terms of efficiency, and slightly better than Strassen's algorithm too. So this is for like hardware like NVIDIA V100. This is for a TPU version 2, where you get these improvements for standalone matrix multiplication for large matrix sizes. Now, so the way we do this is essentially by doing one step of our algorithm, and then we don't essentially do recursion over our algorithm. So you can think of our algorithm as a smarter way of decomposing of a large matrix into smaller blocks. Okay, the idea is that these hardware are actually like very much optimized for doing medium-sized matrix multiplication. So the idea is to try to decompose the large matrix into smaller matrices and then use the standard algorithm for this hardware. So what was interesting also is that the algorithms that we found are quite specific to the hardware considering, in the sense that if you try to optimize for GPU and then try it on TPU, it would be much worse than if you optimize for TPU, an algorithm for TPU, and then try it on TPU, as shown on the right plot here. Okay, so that's my last slide. Maybe just 1 minute for concluding. So the inspiration behind this work was that we developed these very complicated agents that are able to do fantastic, that are able to play fantastically really on chess, Go, and so on. And we wanted to really like see how can this, what is the potential of this in very like difficult combinatorial problems and algorithmic discovery problems. I hope I convinced you that machine learning has an important role to play in tackling these fundamental problems. Now, obviously, there is some limitations to this approach, which I talked about today. In particular, the discretization. So we discretized the set into a finite set. Sorry, we discretized like the whole real numbers into a finite set. For example, -1, 0, 1. So that's a limitation if you consider infinite groups. In the case of finite fields, that was we considered all the field. And also, there is no optimality promise in the sense that we do get an upper bound on the rank, but we don't get any lower bound. What I'm most excited about this kind of approaches is their generality. So as I said, it can be applied to bilinear operations. We think it's also applicable to discovering algorithms for other tasks, and more broadly, really, it can be applied to tackle other search problems. In terms of spaces, we saw that it can be applied to finite fields, where sometimes applying existing combinatorial approaches are really difficult and can go really beyond that. And as I said, in terms of objective functions, it can really model any arbitrary rewards, like as complicated as runtime, which I showed here. And this is, I think, quite exciting in terms of, I think, applying this approach to many other domains. Thank you very much. So that's it for my talk.
Yeah, thank you very much for this very inspiring talk. We have now time for some questions. So maybe I will start with one. So how scalable is this approach? So I think you showed like results for 5 times 5 times 5 matrices. Can you go higher, and like what is the training time, like how much compute do you need to train to optimize it?
Yeah, so we considered like tensor still 555, so of size 25 by 25 by 25. We think we can scale till 100 by 100 by 100, but beyond that, it would really be difficult, I think. In terms of training time, so we trained one agent to solve all these different problems, and it took about a week to get the whole table done, essentially.
For the 5 times 5 times 5, or for smaller?
Yeah, for the whole table, because we trained this one agent, right? Yeah.
Okay, so this is quite okay, I guess. Mm-hmm. So another question. I mean, I'm mainly interested in explainability, interpretability. So I wonder, like, have you looked at this neural network? So what did they learn? Can you get a clue, like what do they represent? What does this intermediate layer do to do this very efficient decomposition?
Unfortunately, we haven't really looked at that, because there is the added complexity of, like a Monte Carlo tree search. It's not only a neural network, it's, like a neural network plus a search together. So it's even harder, I think, to interpret this. I think there is some work. For example, I'm trying to interpret AlphaZero to chess. Mm-hmm. So maybe that's one avenue for interpreting that. But currently, we haven't done much in terms of interpreting that particular network we got for this problem.
Mm-hmm, mm-hmm. Yeah. And then you showed like this nice pattern for this very specific like types of matrices. So can you interpret like the algorithm which is coming out? I mean, does it make sense geometrically, or can you like refer to something?
Yeah. So it's a good point. Yeah. So for this one, like what I showed here is essentially like one particular result for each n, but actually, like for each n, as I said, you get a lot of different algorithms. So we had to ourselves, like to look at the different results and then try to see if there is a pattern amongst them. So this was a human step in this particular case, where we saw this particular result, and then we had to we could extrapolate it really for any n, and then here we had to prove the correctness so we kind of like extracted an algorithm from this particular decomposition from which we proved correctness. Now, this is different a bit from matrix multiplication, because matrix multiplication, you can, like, whenever you get a decomposition for any even small size, you can recurse over it. For this particular bilinear operation, there is no possibility of recursion.
I see.
Right? So that's why we had to do this extra human step of trying to interpret what do these decompositions look like, and to see if there is any pattern, and then we had to go through this generalization ourselves. And that answers your question. Yeah.
There is a question from the audience. So, like, how would the complexity of a brute force search compare to what you spent on training your models?
Yeah, so even for small tensor sizes, like for example, I think 3 by 3, the number of possible algorithms exceeds the number of atoms in the universe. So it's really difficult to like, you cannot enumerate everything, obviously. So yeah, it's like, I mean, you can do a back of the envelope calculation, but it's essentially like exponential with respect to the number of entries you have. So for example, let's say you have a 16 by 16 by 16 tensor, you allow three entries for, like, 3 values for each entry. So you have 3 to the power 16 times 3, and then you need to find you know, like a rank of 40 decomposition, for example. So you take it to the power 40 again. So it's the numbers become quite scary very quickly.
I have another one. I mean, in mathematics, there are like a lot of such, like, problems, for example, with prime numbers or prime number twins. So do you think you can at some point also, like, adapt this kind of philosophy to also investigate or maybe solve some of these problems?
Yeah, I mean, so you mean like factor a number into prime numbers, for example?
Yes, for example, or of
yeah, it has
the next prime number twins, or like whatever. I mean, there are like these kind of a lot of these problems which are easy to understand, but are difficult, like, to really compute and show.
Yeah, that's a good point. So we haven't done anything in this direction yet, but yeah, I think, as I said, some of the methods are applicable to potentially these problems. But yeah, we will be starting to look at these other problems.
And do you think you can also, like, so I very much like this combination with this runtime and maybe, like, also other criteria. Do you think you could also use these kind of techniques to, I don't know, to design better hardware, to really guide also, like, you said that on different hardware platforms you got, like, different kind of algorithms. So I think this is something which is has a lot of potential to also, like, build maybe better hardware or build algorithms which are much more adapted to the underlying hardware.
Yeah, definitely. I think once we have, like, automated this procedure, then you can adapt the algorithm for the hardware, but also potentially adapt the hardware for the algorithm, right? So you can do it in a loop, where, again, like, the hardware is probably something that you can automate it, and you can consider, like, both things and see, like, what is the best hardware for this. So I think it's very exciting times to automate the two things simultaneously. And I think we'll be starting to see a lot of papers in that space.
Great. Then I would like to thank you again, as Hussein. It was really, really an exciting talk. And take care. Bye-bye.
Thank you very much. Bye-bye.
For participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, Try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
Mm-hmm.